Our goal for this video is to set up an integral that will allow us to calculate the volume of something called a spherical cap. So I've drawn some pictures here. The picture on the left is sort of a standard diagram that you see when you're talking about spherical caps. What I mean is I want to find the volume of this sort of region. It's like a three-dimensional region up top. On the right, I've just drawn a straight-on view as if it's not three-dimensional. This cap is the same as that cap. It'll just be beneficial to us to think about it in 2 dimensions and do some geometry there. So I'm going to set up an integral for this thing, and I probably won't evaluate it. I'll leave that to you. And hopefully this will help with some tricky integration problems that we're encountering in Calc 2. So how should I start? Well, okay, here's the diagram. If you're doing one of the homework problems for this class, then the diagram actually looks a little different. It'll be a sphere and there's a cap on the bottom, and it's talking about sort of like filling this with water. And it gives a specific height to this. It says like h equals a quarter of the radius. Okay, so you can just as easily do that once we've finished this more general case. This general case will be more helpful, I think. And all I've really done is I've just flipped that upside down, but it's the exact same if I want to find this volume down here, or if I want to find, you know, this cap on the bottom. It's symmetrical. So it'll be nicer if I work with it this way. So let's get started. The first thing I want to think is I'm going to be slicing, so horizontal slices of this sphere, starting at this yellow circle here, and then moving upwards, right? So maybe I'll do slices in red. So I'm going to go up from, you know, whatever this y value or z value, whatever that height is, up to this height. And I'm going to slice along the way. A general slice will look something like this. It's kind of awful, but a general slice will be a circle. Okay. So you should be thinking, okay, I'm slicing along. Let's just call this the y-axis for ease. So there's x, there's y. I'll draw the same sort of thing on this diagram. Here, that circle, I'm looking at it straight on, so I'm just going to see it as like a flat line sitting inside that cap. And so what I want to do is I want to integrate the areas of all of these red circular slices. Okay, of course, the area here is going to depend on y, because depending on how high we go, the circles get smaller. And the area is going to be pi times, I'll use little r. Again, little r is going to depend on y. Little r is going to be this radius. Maybe I'll draw it in white. The radius of the red circle. Right, so different from capital R, which is just the radius of the sphere that we're dealing with. Okay, so that's going to be our area. That's what we're going to integrate. So, okay, volume is just going to be integral. And what are our bounds going to be? So I'm definitely going to stop at capital R. But where should I start? What's the lowest level? Well, this yellow line or this yellow circle happens at height capital R minus h. Right, so it's a little weird. It doesn't tell you what this distance is, but you figure it out by saying, okay, radius of the big sphere is capital R minus the cap height of h. So I'll start at R minus h and then integrate up until I get to capital R, which is the top of the sphere. Okay, and then the thing I'm going to integrate is just the area, and I'm doing slices along that vertical axis, which I'm calling y. Okay, so the question is, what is the area of that circle? Or looking over here, we know it's pi r squared, but what is r? What is little r? Some function of y. So this is where this drawing is going to be useful. What I'm going to do is I'm going to, let's use, maybe I'll go back to red. So for this particular slice, right, this red line that we're looking at, I want to figure out, this will basically be little r here, like this half length. Okay, so that's little r. And I want to find out an equation for that in terms of y and maybe some other things. Okay, so I'm going to say that, let's say that this height here, well, if I'm integrating along y and I'm slicing as y increases, this is just my y value. Don't get confused with this. This is just the label. Maybe I'll erase these labels to not confuse you. So yeah, as I'm integrating along y, right, that's the height of the slice I'm currently adding up. So labeling that y makes sense. And like I said, the top is r, and then you might think, oh, I could make a triangle out of this. A right triangle in particular. Maybe I'll move this r elsewhere. So that distance, little r. And then, okay, right triangle, we can apply Pythagorean theorem. And this is capital R, certainly, right? Because the radius of the blue sort of hemisphere is constant. It's just capital R, right? It's the same as this. So even though it's not, you know, this line or the y-axis, it's the same length. So I have that. I said my goal was to solve for little y, so little r. Little r is a function of y, is going to be by Pythagorean theorem. You can work it out bit by bit if you want. I'll just jump to the answer. Square root of the hypotenuse squared minus the other side squared. So this can be plugged in here for our area. And lo and behold, we get an integral that looks like this. Again, r minus h to r, because we're just focusing on the cap. The area becomes pi times this thing squared. So square root of big R squared minus y squared. And I'm integrating with respect to y because that's the direction I sliced things. So that's our integral. Keep in mind, r and h are effectively constants. So treat them as constants when you integrate this thing. Keep in mind you're integrating with respect to y, not either of those things. So yeah. What you should get out is a pretty nice formula if you simplify things. And then at the end of the day, you can go in and say, you know, instead of calling this height h, I can call it, you know, for the case of the problem we're talking about in the homework, that was, I think, r over 4. Right? So you can go in and plug in r over 4 if you want, and that'll give the answer to that particular problem. But this works in general, gives you the volume of any spherical cap, no matter what capital R and H are. So that's it. I hope you found that helpful, and I'll see you next time.